Hello and welcome to another lecture of 6837, or at least another lecture segment. Now that we've established a few of the basics involving metric embedding problems, we're going to switch gears and talk about practical algorithms for doing this in practice. So in this lecture segment, we're going to specifically focus on probably the most popular embedding problem, which is to take a general metric matrix and embed it specifically into Euclidean space. Right, so the target of our embedding, right, hopefully our map will be nearly isometric, is just Rn equipped with the L2 distance metric. So if you recall from our last lecture segment, essentially what we're after is an isometry, right? A map from one metric space into another that preserves pairwise distances. Of course, in practice, we rarely can compute an isometry exactly, like we had a counterexample last time where it wasn't even possible. So we're often going to have to satisfy ourselves with an approximate solution to this kind of a problem. But before we even talk about approximation, I thought I'd start with what might be considered the easiest possible case. And that's sort of just closing the loop when it comes to Euclidean distance embedding. So here's the basic problem we're going to set up. Suppose that I had a bunch of points xi, and they're embedded in some space Rm. And I compute from those xi's a pairwise distance matrix, or just for convenience, in this case, we'll say a pairwise distance squared matrix, which we'll call P. Right? So element ij of our matrix P is the distance between xi and xj squared. Now, there's going to be n points. So Pij is an n by n matrix, or rather P is an n by n matrix. And each of the points will be an Rm. We're not going to make a whole lot of assumptions on the dimensionality. We'll see that it doesn't really matter. But essentially, the very first computational question we might answer is, suppose that I forgot the xi's. So I started with some xi's, I computed this matrix P, and then I forgot the xi's. The question is, can we recover them from the matrix P? So in other words, I know hiding inside of P are the pairwise distances between our points. I just forgot where our points are. And somehow, this is the simplest question to ask, because if we can't solve this problem algorithmically, we're going to have a lot of trouble with metric embedding more generally. And in fact, we can't solve this problem exactly the way I've stated it, right? So for instance, if I take the x's and I add a constant to them, well, what ends up happening? You know, so xi minus xj becomes xi plus c minus xj minus c. So adding a constant vector to our points doesn't affect their pairwise distance. In fact, neither does rotating them, for example, multiplying all the points by an orthogonal matrix. So we're going to have to relax our problem a little bit. We're going to say, given Pij, and given the fact that Pij came from pairwise distances, maybe I can't recover the x's that I started with, but I can recover some set of x's that also has the same pairwise distances. In fact, we'll see that they're the same as our original x's, just up to rotation and translation. Okay? So that's our basic task. Again, to summarize, we had a bunch of points in Euclidean space, we computed their pairwise distance, we forgot the points, and now we want to recover their positions again, at least up to rigid motion. So in order to do that, it turns out that it's quite convenient to work with a slightly different matrix, which is really hiding inside of this P, we'll see in a moment. And that is a matrix with a very famous name. It's called the Gram matrix, which is just X transpose X. So I guess I haven't actually defined X for you, so let's do that now. So essentially, remember that I have a bunch of data points. We'll call them xi, right? So there's x1 through, be careful with our indices here, xn, xn, and these are embedded in Rm. I just got paint all over myself. Yikes. I'm going to pause for a moment. Okay, so in that case, I can construct a matrix big X, right? And so essentially big X is just going to have columns as the xi's. Ah, man. Like this, right? So I can write big X is going to be the matrix whose first column is x1, second column x2, and the nth column is xn. Okay? So then we're going to define the Gram matrix, G, Sorry, I got paint all over myself, and now it's all over the board. I can write the gram matrix G as just equal to X transpose X. Okay, so what are the elements of G? Well, if you kind of work through, our definitions here, then what you'll see is that Gij is nothing more than the dot product between data point I and data point J, right? And that's just because, remember, dot product between two vectors is the same as like Xi transpose times Xj. So what we're going to find is that it's pretty straightforward to recover an embedding from the matrix G. So essentially, our solution to the problem on the previous slide is going to happen in two steps. Our first step is going to be to recover G from P, and then we're going to recover our embedding from G. Hopefully that makes some sense. My apologies for a little bit of pausing and switching markers here. Okay, so the first step is going to be to recover G from P. So let's move our formulas into the corner here. We're going to get G from P. And remember that we only can figure out our points X up to a rigid motion. Right? Like if I added a constant vector to all of the X's, then we couldn't recover that constant vector from P because it doesn't affect pairwise distances. So in particular, we're going to recover a version of G with the assumption that P was computed between points that sum to 0. Okay, so we're going to add an assumption that the sum over I of xi is equal to 0. And hopefully you see why that's okay. Again, remember that Pij here is equal to xi minus xj squared. And of course, that's the same as xi plus a constant minus xj plus a constant for any constant. And so we really don't expect to be able to do better than to recover our point cloud, certainly up to a constant shift here. So I'm going to just shift everything so that they sum to 0. Their center of mass is 0. Okay, so now that we made that assumption, let's see if we can figure this out. So let's expand our expression for P. So again, Pij is equal to the norm of xi minus xj squared, as we've written a number of times. And now we're going to expand the square. So this is equal to the norm of xi squared plus the norm of xj squared minus 2 times xi xj dot product. Okay, so here's the nice thing. Remember that our matrix G is just given by the dot product between every pair of vectors. And now we can see that essentially all we have hiding inside of this squared expression here is a bunch of dot products, right? So really, Pij is equal to Gii plus Gjj minus 2Gij. Incidentally, G is a symmetric matrix, right? I could have written minus Gij minus Gji, but that's not necessary. Okay, so this is an indexed expression. Let's see if we can write it in slick matrix vector notation. So in order to do that, let's take a look. So these are diagonal elements of the matrix G. And then this is just from G itself, right? So what do we see? We see that P is equal to minus 2G plus this thing involving the diagonal of G. Now, let's see if we can be a little more specific than that. In particular, what's going on here? So the Gii term does not depend on J at all, right? So it's kind of like constructing a column vector and then just repeating it a bunch of times. And then similarly, the Gjj term is like constructing a row vector and repeating it a bunch of times. So overall, what we find is that we can write P is equal to, well, first let's take care of the minus 2G part. That's the easy part. And now what are we going to get? Well, we can think of this as taking the diagonal of G and repeating it horizontally and vertically, right? So this looks like the following. It looks like diagonal of G. So this is the vector of elements along the diagonal of G. So like G11, G22, G33, and so on. Multiplied by the vector of all ones transposed. So I'll let you work out on scrap paper what that does. Essentially, if you take a vector and you multiply it by the vector of all ones transpose, you're just taking that vector and copying it a bunch of times. And similarly, you can copy it vertically. So you'll get 1 diag G transpose. Okay, so now we have a relationship between P and G, but it doesn't quite do what we wanted, right? Because we wanted to get G from P, but we currently have a way to get P from G, so we have to invert these two things. Okay, so let's see if we can do that. Essentially what we're going to do is we're going to make, our assumption here, right, that the sum of the x's is equal to 0 is going to be what saves the day. So a different way to notate that in our nice matrix notation is just to say that our matrix X times the vector of all ones is equal to the vector of all zeros. Hopefully you see that, right? This just comes directly from our expression for big X here. And if I pre-multiply this expression by X transpose, remember that G is equal to X transpose X, what I get is that G times the vector of all ones is equal to 0. Remember that G is a symmetric matrix, so that means that also G transpose times the vector of all ones is equal to 0. Okay, so these are going to be the expressions that allow us to do something a little bit nicer. So again, remember our story. Our story is that P, the elements of P are pairwise squared distances between points in Euclidean space, and the elements of G are their dot products. And without loss of generality, we can always assume that our points sum up to 0 by just adding a constant. And so essentially our task is going to be to recover G from P, assuming that our points sum up to 0, and then we'll get the embedding from G using basically an eigenvalue problem. Okay, so here's what we're going to do. We're going to make a sneaky definition. Okay, we're going to define a useful matrix, J, and J is going to equal the identity matrix minus 1 over n, 1, 1 transpose. Okay, so let's make sure that we know what this thing is. So J here, the identity matrix leaves something alone. 1, 1 transpose projects onto the constant vector. So this is kind of like projecting onto the orthogonal space to the constant vector. And the reason that we are going to like working with J is that, well, everything should be kind of orthogonal to the constant vector because we've assumed that our points sum up to 0. Okay, so now we're going to do a sneaky calculation. What we're going to do is we're going to compute minus 1/2 J transpose Pj. Okay? So again, what we're going to compute is minus 1/2 J transpose Pj. And we're going to try and figure out that this thing is equal to, well, G. I already gave it away on the screen here. Okay, so how do we do that? We're going to follow the Toucan Sam approach to mathematics here and just follow our nose, okay? So, by the way, notice that this matrix is symmetric, right? Identity is the symmetric matrix, and this guy, if I transpose it, just flips those two ones. Okay, so, right, so this is equal to minus 1/2. Now we need the J transpose, so that's identity minus 1 over n, 1, 1 transpose. Okay. Notice this transpose is optional because, again, J is symmetric. We usually write this expression with a transpose just so it kind of looks symmetric. And now we have P, but we have an expression for P, right? So this is minus 2 times the gram matrix plus the diagonal of G times the vector of all ones, transpose, plus the vector of all ones times the diagonal of G transpose. Okay, so that's our P term here. And then we have J again, right? So that's another identity minus 1 over n, 1, 1 transpose. Woof! I just barely fit it in before these expressions here. Good. Okay, so this expression is ugly, and essentially what we need to do now is just a giant, boring calculation. I'm going to see if I can do it without my notes, and then there's high probability I'll have to go back and edit this video, but let's see what happens. Okay, so first, let's basically multiply the first two terms here. So we'll leave the minus 1/2 on the outside. And first we have the identity term, so we get a minus 2g plus diagonal of g times 1 transpose plus 1 times the diagonal of g transpose. Okay, and now we have a minus 1 over n 1, 1 transpose to multiply by this whole thing. Again, remember we can ignore this transpose here because the whole thing is symmetric anyway. Okay, so what do we get? Well, let's see, we have a minus 2 and a minus 1 over n, so this is a plus 2 over n times 1, 1 transpose g. Okay, and then we have a minus 1 over n, 1, 1 transpose times the diagonal of g times another 1 transpose. And now we have another minus 1 over n, 1 transpose. And then we're going to have a 1 again, diagonal of g transpose. Going by the seat of my pants here, folks. Hopefully I'm not making any mistakes. 1 over n, 1, 1 transpose. Okay. So if I did this right, then essentially all we needed to do was multiply these two terms out. So did we do this right? The first one is just a copy. The second one we have a minus 1 over n. We have plus 2. Yeah, so this looks good so far. Okay, so now let's see if we can simplify this a little bit before we dare to do the next piece of our product. I'm sweating already. There's too much math here. Okay, so first of all, 1 transpose 1, this is the dot product between the vector of all 1s and itself. So this thing is equal to n. So the 1 over n and the n are going to cancel. So that's good news. Okay, what else can we do? Well, remember that if I multiply g by the vector of all 1s, I get 0. Here, this is just that expression transposed, so I get 0. Okay, what else can we do? Well, let's see here. Let's look at this expression, okay? What's going on here? Well, if you think about it, we have the diagonal of g. Well, can we do much with that? Yeah, we can. Okay, so this is the vector of all 1s multiplied by the diagonal of g as a vector. Okay, so if we think about it, those two terms together are the trace of g. Okay, and then we have a 1, 1 transpose on the outside. Okay, and then finally, aha! So we have a 1 over n times an n, so these two terms cancel, and what we're left with is 1 times the diagonal of g, with a minus in front of it. Here's 1 times the diagonal of g, the plus in front of it, so those two terms cancel. And now we're cooking with gas. Now we're in okay shape. Okay, so we have, well, the minus 1/2 is still there. We have a minus 2 times g. And now, let's see here. So we have the diagonal of g times the vector of all 1s transpose. Nothing we can do about that. Like that. So that's this term here. This term canceled with that one, so it's not here. This term was equal to 0. This guy is equal to minus 1 over n times the trace of g times 1, 1 transpose, like that. And I believe that is everything we can do. I guess we could factor this out if we really wanted, but whatever. Okay. And this is times the identity minus 1 over n, 1, 1 transpose. If you haven't figured it out by now, your instructor is sweating right now, because usually I do this stuff in advance, and this time we're just doing it live. Okay, so now, sadly, we have to do more multiplication. Okay, so what do we get? We get minus 1/2 in the front. Okay, so first we'll do the identity term, and then we'll do this extra guy. Okay, so for the identity term, again, we'll get minus 2g plus diagonal of g times 1 transpose minus 1 over n times the trace of g times 1, 1 transpose. Okay, now we need to do this minus 1 over n, 1, 1 transpose. Okay, so let's see if we can do a little bit of this live. First of all, remember that g times 1 is equal to 0, so we can skip that term. And now what are we going to get? We'll have minus, we have a 1 over n, and now we have a diagonal of g 1 transpose times 1, 1 transpose like that. And then finally, for our last little piece here, we have a minus times a minus is a plus 1 over n squared times the trace of g, like that. And now we got all kinds of stuff. We have 1, 1 transpose, and then a second 1, 1 transpose. Okay. So let's see what we can simplify here. So if we stand back 10 feet, maybe 20 feet, then, well, I claim that we should be able to cancel, well, first of all, we can take a look. So 1 transpose 1, that's equal to n. That cancels with the 1 over n. So this is really just the diagonal of g times 1 transpose with a minus in front of it. Here's diagonal of g times 1 transpose with a plus in front of it. So these two terms cancel. That's good news. And I claim these two terms cancel as well, because here, again, we have 1 transpose 1 is equal to n. That cancels out one of the factors of 1 over n. Then what we're left with is 1 over n trace of g, 1, 1 transpose, the plus in front of it. Here's the same thing with a minus. So those two go away. And what we're left with is minus 1/2 times minus 2g, which is g. I'm going to put a victory mark because I'm sweating and I'm nervous and I got this calculation correct, even though I didn't write it in my notes. Okay, so what did we just show? We showed the following, that if we have this matrix of pairwise squared distances, then we can recover the gram matrix of a collection of points whose distances are these ones and which are centered at 0, right, where the points average to 0. And the way that we do that is just by starting with p and conjugating with j and multiplying the result by minus 1/2. Okay, so what does this mean? That means if we have g, we have j. If we have g, we have p. If we have p, we have g. So, you know, we can work with either one and be happy that we can go from one to the other, right? So here we go from g to p. From here we go from p to g. Okay, so our next task is going to be to recover an embedding from g. So in other words, we want to show that g is equal to x transpose x for some set of points x. And if we can do that, then we're in good shape. Okay, so let's erase this messiness. It's making me nervous just looking at it. And then we'll continue by getting x from g. Okay, so our second task of recovering x from g is actually, I would argue, easier, or at least less nerve-wracking. Okay, so how are we going to do that? Well, let's make a few observations about g. So first of all, because g is written as x transpose x, it's immediately clear that g is a semi-definite matrix. And moreover, we have that the rank of g is equal to, well, at least upper bounded, I suppose. I guess there's a linear dependent case you have to be careful about. But it's upper bounded by the min between m and n, right? I could have a ton of data points, but the rank is overbounded by the dimensionality, and vice versa. If I have really high dimensional data, then if I don't have enough data points to fill those dimensions, then maybe that's what saturates it. So in particular, one thing that I can do is just use eigenvalue factorization here. And I can write G is equal to Q lambda Q transpose. So one thing that I can do is remove 0 eigenvalues. So I don't necessarily have to assume that Q here is square. What I can assume is that Q is a tall matrix, meaning that its columns are orthonormal. So Q transpose Q is equal to the identity, right? Because this is a smaller matrix, right? This is tall by short. But I may not make the additional assumption that Q times Q transpose is equal to the identity. So here's what I'm going to do. I'm going to define my embedding to be the square root of lambda, which is just element-wise square root, because we know that our eigenvalues are non-negative, multiplied by Q transpose. Okay, so if I compute the gram matrix of this, what am I going to get? Well, I'll get Q times square root of lambda times square root of lambda times Q transpose, which is exactly G. So what have we done? Well, let's write it out maybe. So G is equal to x bar transpose x bar. This is really the gram matrix of the points that we just proposed, but we want to show that this is equal to, our x, or at least x transpose x. Okay, so, well, we're going to get a Q from the Q transpose times the square root of lambda. Remember, this is a diagonal matrix, so it doesn't matter if it's transpose or not, times the square root of lambda again, times Q transpose, right? So these two guys together, these are just lambda. Which, okay, so we have Q lambda Q transpose, and this is equal to our gram matrix. Okay, so if we unravel our story a little bit, what did we just do? Well, I defined for you a point set x bar, which was obtained from a matrix G. What we showed is that x bar transpose x is equal to G. Okay? So in other words, G is the gram matrix of this particular set of points x bar. But we also showed in sort of number 1, which I've erased from the board, that G can be obtained from P for pairwise squared distances. So overall, our construction tells us how to get an embedding x bar based on our pairwise distance squared matrix P. What it doesn't say is that x bar is equal to x, and in fact, they can be shifted or rotated from one another, because that information is basically just thrown away. Okay, so let's summarize what we've done, and we can do so by writing down an algorithm. And this algorithm is extremely famous. It's called classical multi-dimensional scaling, or MDS. And it happens in 3 steps, which are given on the screen here. Conveniently, I have managed to use the same notation on the board as we had on the slides. So what we do is, as input, we're given a pairwise squared distance matrix, and our task is to re-embed our points. We first perform a step called double centering, which is to compute a matrix G equal to minus 1/2 J transpose J. And we showed that G is the sort of corresponding gram matrix to our squared distance matrix P. Then in step 2, we factor our matrix by writing Q lambda Q transpose. And then finally, our embedding x bar is equal to the square root of lambda times Q transpose. Now, if I keep every single non-zero eigenvalue of G in step 2, then actually there's an equality condition, right? X bar really is an embedding that has pairwise squared distance matrix P. But what's common practice, because I'd like to have a low-dimensional embedding of my data, is maybe to truncate x bar to the first few sort of dominant eigenvalues. And you can actually prove some nice results that say that that's a pretty good approximation of the full MDS embedding. So now we have it. This is our first embedding algorithm under the Euclidean squared distance assumption, right? So we go from a squared Euclidean distance matrix P all the way to an embedding x bar, and we even along the way proved that this isn't an approximation. X bar is truly an embedding of our data that has the pairwise distances we want, so long as our original matrix came from pairwise squared distances. I feel like I'm talking in circles, but hopefully that's pretty straightforward. So here's an example of what that looks like. So this MDS technique is used a lot in data analysis. This is a very common thing to do. So for instance, here we have voting data. I believe this is from US Congress. So red and blue correspond to Republican and Democrat, I guess respectively. And you can take every congressperson and represent them as one long vector of every single vote that they take. So we're going to put a 1 every time they vote, I think yay, a 0 for present, and a -1 for nay. And now I can compute the pairwise distance between every pair of senators, which tells you something about the amount of ideology they have in common. Now this is extremely high dimensional data, right? The dimensionality of our original embedding is equal to what? Like the number of votes that all the senators took, or all the congresspeople. But if I just take the top 2 eigenvectors in our embedding x bar here, then what I get is this really nice visualization. And notice that in one 2-dimensional, multi-dimensional scaling plot, we've managed to capture what's wrong with politics, right? All of the all the blues are on one side, the reds are on another side, and they're far apart, right? And probably if you looked at the identity of the folks in the middle, they'd be pretty much who you would expect. Your instructor will refrain from commentating too much at this point. So let's get some space and then we'll continue. Okay, so now let's continue by making another observation about our MDS embedding, which is going to land us, oh boy, is going to lead us to a technique called landmark MDS. Okay, so let me summarize a few facts that we had so far in lecture. I'm nervous, this marker is going to start dripping paint everywhere again. So remember that we know that q times the vector of all 1s is equal to 0. Remember that q is from our factorization of the Gram matrix. And we know that because we assumed that all of our points in our embedding sum to 0, right? And if we pre-multiplied this expression by the square root of lambda, we'd get our embedding, roughly. And moreover, we already wrote on the previous screen that q transpose times q is equal to the identity. We're not going to assume that q times q transpose is equal to the identity because q may not be square in the case where there's 0 eigenvalues. Okay, so here's what we can do. Oh, and just for a reminder, we have that p is equal to -2g plus the diagonal of g times the vector of all 1s transpose plus the vector of all 1s times the diagonal of g transpose. Okay, so and finally we factored g is equal to q lambda q transpose. Okay, so I think this is all of the sort of facts that we're going to need for the next step of our proof. So now what we're going to do is we're going to start with x bar, and we're going to substitute in some of the things here to get kind of an interesting expression. In particular, we're going to have x bar, we're going to post-multiply it by our pairwise squared distance matrix P. Okay, so what is x bar? Well, remember that it was the square root of lambda times q transpose. And now let's plug in this expression for P. So we're going to have -2g, which is q lambda q transpose, plus the diagonal of g, which is q lambda q transpose, times the vector of all 1s transpose, plus the vector of all 1s times the diagonal of g, which is q lambda q transpose transpose. Whew. Okay, so now what we're going to do is multiply out this expression and see what happens. Okay, so the first term we're going to get, well, let's see. So we have a q transpose times a q. Remember, that's equal to the identity, so those go away. We have a -2 in front, so there's a -2. We have the square root of lambda times lambda. So if we do some accounting, that's lambda to the 3/2. And then finally, we have q transpose, like that. Okay. Now let's think about the next one. So I don't think there's a whole lot we can do with this quite yet, but maybe I'll just write the square root of lambda times q transpose as x bar again. So we'll say that that's x bar times, well, this diagonal matrix, q lambda q transpose times a vector of all ones transpose. Not a whole lot we can do about that. And then finally, we have q transpose times 1, which is equal to 0. Oh, my apologies. I should have written that because remember that x bar is, there's a q transpose in x bar. Sorry about that. OK. So this is kind of an interesting expression, and we can actually do a little bit of reshuffling here. So let's factor out the x bar on the left-hand side. OK, so we're going to get x bar times, now we have a p minus diag of q lambda q transpose times 1 transpose like that is equal to minus 2 lambda to the 3/2 q transpose. Okay, and of course, remember that lambda times q transpose is x bar. In fact, we keep using that, so maybe we should write it here. Right, so it's the square root of lambda times q transpose. So just for fun, let's factor that out. So we're going to have a negative 2 lambda x bar. So in particular, what this means, if we multiply both sides by the inverse of lambda here, is what? That we'll have that x bar is equal to, sorry, my notes are incorrect, but I'm pretty sure that I'll be right if I do this, is minus 1/2 lambda inverse x bar times p minus diag of, remember this is just G, our gram matrix, 1 transpose. Okay. Now this seems like kind of a circular definition, but this is actually kind of useful. In particular, what it means is that if we extract a column here, so we look at just like the ith point in our embedding, it's actually equal to, maybe I go ahead and multiply the minus out. So we're going to have 1/2 lambda inverse x bar. And now we can think of this as I'll leave the minus, pi minus g, where this is just the diagonal of g, right? So this is equal to that. And pi is just like the ith column of p. So that's all I've done so far. So why did I do that? So I've noticed I've made a sign mistake, and I'm wondering if I should try and fix it now. No. So relative to my course notes, there's a sign mistake here. I'm going to go back and fix this in the written course notes, and for now, it's not going to matter. In fact, if we took our whole embedding and multiplied it by -1, the pairwise distances wouldn't change anyway. So even though I've made a mistake, it's kind of an okay mistake to make. But in any event, up to sign, this is correct. So what does this tell us? This tells us that if I know the ith column of p, remember that p is like the set of squared distances from a single point to all of our points in our data set, then I can recover the point xi from this expression. So now the landmark MDS algorithm does kind of an interesting thing, which is it says, okay, let's say that I go ahead and do MDS on some set of landmark points. Those are the points that are going to be in my matrix P. Now I want to extrapolate that embedding to a new data point that I haven't embedded yet, but I don't want to redo my eigenvalue computation. Then one way that I can do it is to use this expression. So what I'm going to do is just say, okay, well now if I get a new data point, I'm going to compute the corresponding P for that data point. So in other words, just a list of square distances to all of our original set of data, and just plug into this expression. So no recomputation of eigenvalue needed. This is just the embedding of the original data. And use that as the embedding of our new data point. So now I have an online algorithm that can take new points and embed them into the same space that I originally applied MDS to. And this has the nice property, of course, that if I plugged in any of our original data points, pi, I would recover their original embedding. I wouldn't move them by accident. So this technique is called landmark MDS. It's particularly useful if like my data set is really, really big. One thing I can do is randomly subsample my data, embed that, and then use this formula to kind of extrapolate where everything else goes. So that's what you're seeing in the figure on the slide here. So the black points are the ones that were actually embedded using MDS, where their pairwise distances are just distances between those points in 2D. And as we go from left to right, they're adding more and more error. And even with like 3 points, extrapolating this map does a really nice job. And the amount of computation you need is a lot lower, right? Because if I only have like 10 points for my landmarks, then I only have to do a 10 by 10 eigenvalue problem instead of one that scales with the original size of my data set. Okay, so let's erase and then continue. Okay, so far we've derived one algorithm for embedding points given their pairwise distances, and it sort of did so, or at least the way that we motivated it was by kind of closing a loop, right? We started with pairwise distances that were Euclidean in nature, and then showed that we can recover the original points up to rigid motion in this MDS algorithm using a bunch of linear algebra. Now, one thing that we did not show in our discussion was some discussion of error. So for example, if our matrix capital P is slightly incorrect, I didn't justify that the MDS algorithm will give me only slightly incorrect embedding, right? Like for all we know, something catastrophic goes wrong. Now, that doesn't happen to be the case, but what's certainly true is that we didn't motivate or write the MDS algorithm down in what I would call a variational fashion. So what that means is that I didn't write it as an optimization problem, right? Rather, we just wrote a bunch of linear algebra steps and showed that they all, jibe with each other the right way. But a different approach to embedding says, okay, if I want to embed points whose distances look like the distances in a given matrix or data set, then well, I should just write down an optimization problem that tries to do exactly that. And probably the simplest formulation of this problem is something called stress majorization, which is given on the slide here. So here, our input is a matrix D naught, and the entries of D naught, which are D naught ij, are supposed to be the pairwise distances between a bunch of points, or some approximation thereof. And now our output is going to be an embedding X, just like in the MDS algorithm. But unlike an MDS algorithm, in stress majorization, we're just going to write down an optimization problem that kind of measures exactly what we're looking for and try to minimize the objective. So in particular, what do we want? Well, we want that the distance from xi to xj looks like element ij of our matrix D naught. So why not subtract those two things, square, and sum over all pairs ij? And that is exactly the stress majorization objective function that you see on the slide here. Now, one thing that you can check pretty easily is that this is a non-convex optimization problem, right? It might kind of look convex if you're squinting at it, but it's not, because in the inside of the square here is a norm that is not squared. So it kind of looks like the absolute value of x minus a constant, and then that whole thing squared, which has a non-convex shape. But even though this optimization is non-convex and extracting its global optima might be quite difficult, it turns out there's a local optimization algorithm that's quite popular and extremely effective in practice that is also easy to implement. And that's what we're going to derive in lecture next. So this technique is called scaling by majorizing a complicated function, or smack off, which is a really unfortunate name for an algorithm that we are now stuck with for the rest of time. When you guys now go on to propose your Turing Award-winning work, may I suggest not choosing a goofy name for your algorithm like this one, but in any event, even if it has a stupid name, it does happen to be a pretty effective technique for nonlinear embedding of points. So again, in stress majorization, what we do is we write down this objective function here, which is literally just saying, I want xi minus xj to look like d naught ij, so I subtract the two and square. And now we just need to come up with a clever way to optimize this thing. Notice that this isn't actually a differentiable objective function either, thanks to the norm not being squared in the inside of the square there. Okay, so what we're going to do is we're going to start with the objective function here, and we're going to apply some just simple algebra to it to write it in an alternative form. So let's get started with that. Okay, so we'll move this into the corner here. So as with just about every proof that we do in our lectures, we're going to take some squared quantity and expand the square. So let's do that. In particular, we can write the following. So we have an objective function, which is the sum over ij of d naught ij minus xi minus xj, the 2 norm quantity squared. And now let's expand this, this outer square here. So what are we going to get? Well, remember that our optimization variables here are the x's. Right, so the d naught squared term here doesn't actually affect anything. We can just think of that as some constant. Okay, and then what are we going to get? Well, if we look at the other squared term, we'll get the sum over ij of xi minus xj norm squared, like that, right? So that's this second term squared. And then we have a cross term. So we have minus 2 times the sum over ij of d naught ij times the norm xi minus xj. Okay, and that norm is not squared. And so if you're wondering, essentially, you can think of all of the non-convexity in our optimization problem as lying right here, right? That's the non-convex piece. So this is pretty benign. It just looks like a least squares problem. And so the basic observation we're going to make in this Smakov algorithm is we're going to try to upper bound this term using something convex, optimize the upper bound as a proxy, and then iterate. Okay, so let's do some additional simplification just for fun. We're going to label this second term as number 1 here, and the third term as number 2. Okay, so how can we write number 1? Well, so we have the double sum over ij of xi minus xj. We again see something squared, so we should be quaking in our boots until we expand that square as well. So this is the sum over ij. And by the way, remember that we have this gram matrix G which we can work with, which is just the dot products between the x's. Okay, so just like our proof of the MDS algorithm, what do we have? We have GII plus GJJ minus 2GIJ. Right, exactly the same as before. Okay, so of course, we can separate this sum into 3 terms. Let's think about the first one. So this is the sum over ij of gii. So the sum over j isn't doing anything. It's just incurring a factor of n. And similarly for the second one. So what are we going to get? We'll get 2, right, for 2 different terms, n times the trace of g, right, because that's just the sum of gii over I, minus, now we're going to have 2 times the sum over all ij, gij. Okay, so one thing that we know, of course, is what is this sum of an entire matrix? Well, one way that I can write it is that this is the same as 1 transpose times g times 1. Right, because g times 1 is the row sums, and then if I pre-multiply by 1 transpose, then that's the sum of the row sums, which is the sum of all elements of g. This is a 1 by 1 matrix, so it's equal to its trace. So I can write it in this complicated way, if I really wanted to. Okay, and that is the same thing, just by the trace cycle property, as g 1, 1 transpose, like that. So far I haven't done anything too exciting. These are just different trace properties. But now I can combine these 2 terms, right? So this is equal to the trace of g times, well, we have 2ni minus, and then what do we have? 2 times 1, 1 transpose. Like that. Okay, so we're going to give this this thing a name. We're going to call this matrix V. And just to connect it to MDS, if we wanted to, V is really equal to 2 times n times j, where j was the thing we used for centering our data before. Remember that G, again, is equal to x transpose x. So in particular, by the cycle property, we can write this whole thing as the trace of x, v, x transpose. Okay, so this is a nice kind of slick way to write term number 1 in our objective function for this smack off problem. Now we need to simplify objective term number 2. So it would be really nice if stress majorization were a least squares problem, but it ain't. You know, it's not least squares, and the reason it's not least squares is that there's no square in this norm here. And that's too bad. But essentially, when we derive our algorithm, we're going to do a little mathematical sleight of hand. And essentially, what we're going to do is multiply and divide by this term so that it does look like a least squares problem. This is like just a sneaky mathematical trick. So in particular, notice, by the way, that when I equals j, this is just equal to 0. So we can sum just over indices when I is not equal to j. So let's do that. And now, here's what I'm going to do. I'm going to say that this is equal to d naught ij divided by the norm xi minus xj times the norm xi minus xj squared. So I haven't done anything. I just multiplied and divided by this numerator here. Now, the reason that I'm doing that is that now our problem is going to look like least squares. So we're going to kind of treat this coefficient like a constant and optimize for everything else. That's what our algorithm is going to look like. So in order to make that sound a little more formal, we're going to define a convenient matrix that that's going to make our life a little easier. So let's have a little sidebar here. We're going to define B, which is a matrix that is a function of x, with the following properties. So it's going to have elements bij of x, satisfying the following. So when I is not equal to j and when xi is not equal to xj, it's just going to be this coefficient here. Is that right? I made a bit of a typo in my handwritten notes before class. Yeah, that's right. So it's going to be minus 2 d naught ij divided by xi minus xj, like that. If I is not equal to j and xi is not equal to xj. It's going to be 0 if I is not equal to j and xi equals xj. So in other words, we just have to be a little careful to account for the case when there's no contribution here. And then finally, it's going to equal to minus the sum of over j of bij, where j is not equal to I, if I equals j. So in other words, this third term here is just making the row sum to 0 by putting minus the sum of the off-diagonal elements down the diagonal of B. So if I make this definition, which hopefully I got right despite the mistake in my notes here, okay. So I'm actually, I think I'm going to leave this minus 2 here just for fun. So in that case, I'm going to get rid of this minus 2. Doesn't really matter. Either way, we can define our algorithm. Constants don't matter. Okay, so in this case, this is equal to minus 2. That's a 2 times the trace of x times b of x times x transpose. And why is that? Well, it's basically, at this point, just an identical argument to what we did on the left-hand side. All we did was just absorb all of the annoying math into this little coefficient matrix B. Okay, so at the end of the day, what have we done so far? What we've done is we started with our objective function for stress majorization on the upper left, and we showed that it's equal to the sum of three terms: a constant term, a pairwise difference term, which is just a nice convex quadratic, which is equal to trace of xv x transpose, and then finally we have a third term, which is going to be minus 2 times x b x transpose, where b is now a function of x. So essentially what I did is took all of the non-quadratic part of our stress majorization problem and I just hid it in this matrix B. Okay, so let's clean off the board a little bit, and we'll take a look at. Actually, if you don't mind, maybe I'll cover up things a little bit with this slide here and leave my handwriting here. So hopefully you can see. Well, there's a small typo that we'll address later in that I put a minus 2 here and a minus 2 there. I think that may actually be correct. Is that right? I'm not 100% sure, but we're all grown-ups in this class. So one thing that I'll ask you all to check at home, oops, I'm realizing I'm writing behind the board here. I'm not 100% confident if there should be a minus 2 here or not. I made a small mistake, but regardless, what we want is to get this expression here. And the main thing that matters is that we're absorbing the 1 over the difference term into this matrix B. So I apologize. As always, your instructor is terrible at sign mistakes and constants, and you're seeing both of those here. But you know, this is a graduate course, so a little bit of sloppy math is excusable, I think. Okay, so let's erase the board and remove the evidence of my arithmetic, and we'll go with what's on the screen here, which is our basic setup. So again, we define a matrix B, which is a function of x, and the elements of B look like 1 over norm with a bit of a constant, maybe not. I'll double check this. And that's a really critical piece. And the point here is that we can write our objective as in terms of B by writing a constant plus trace of xv x transpose minus 2 trace xb x transpose. Okay, let me erase, and then we'll continue explaining what else is on the slide here. Okay, so a little bit of arithmetic mistake aside, our basic high-level point here is that we wrote something that almost looks quadratic as an objective function for our stress majorization problem. And now the next trick we're going to do is to write down sort of a quadratic proxy problem and solve that as part of our optimization. So we're going to make a quick definition, which is a function that I'm going to call tau. So here's tau. And tau, rather than being just a function of x, is going to be a function of two matrices x and z. Okay? And essentially, what I'm going to do is I'm going to write tau is equal to the constant term we had before. Right? This is just a function of d naught plus the trace of x v x transpose. Okay? So this is starting to look like our stress majorization objective term. But now we're going to do something a little bit sneaky, which is we are going to subtract here minus 2 times the trace of x. But now rather than putting b of x, x transpose, that would give us our objective function, we're going to do b of z, z transpose. Okay? So notice, right, that if I put tau of x comma x, what I get is the objective function that we're trying to optimize. So somehow what I've done is defined a function of two variables so that if I put in the same thing twice, I get the function I'm going to optimize. And now what I'm going to prove is like a sneaky little lemma here, which is that essentially tau of x comma x, which is our objective function, is upper bounded by tau of x comma z for any choice of z. And moreover, with equality only when the two things are parallel to each other. So, parallel, like, one is a multiple of the other. All right, and so we're going to prove this lemma first, and then we're going to show how it leads us to a pretty easily implemented optimization algorithm. Okay, so let's go ahead and prove this lemma here. Okay, so again, remember that our goal is to show that tau of x comma x is less than or equal to tau of x comma z. So in order to do that, what we're going to do is make use of a corollary of Cauchy-Schwarz inequality. So in particular, here is our review. So here's Cauchy-Schwarz inequality. In particular, we're going to apply it to a very carefully chosen pair of vectors. We're going to say, okay, we'll take the difference between xi and xj, dot producted with the difference between zi and zj. Now, by the Cauchy-Schwarz inequality, what we know is that this dot product is upper bounded by the norm xi minus xj times the norm zi minus zj. Okay, so a different way that we can write this, we can reshuffle a little bit and say that this is equivalent to, at least in the case where we're not dividing by 0, we know that xi minus xj, the 2 norm, is upper bounded by xi minus xj dot product zi minus zj divided by the norm of this thing. Now, notice, by the way, that if I put this norm just around this underneath the second term, then I'd get a unit vector for what it's worth. Okay, so essentially what we're going to do, what we need to do is examine the relationship between the left and the right-hand side. So if we go back to our definition of tau for just a moment, notice that when I compare tau of xx and tau of xg, the first two terms of the definition of tau remain the same, right? So it's just the third term that we have to worry about, right? And so in particular, we want to show what? The trace of xbz transpose is actually, let's see, less than or equal to the trace of xb of x transpose because of that minus sign there. Okay, so let's see if we can prove the inequality that we need. Okay. So let's start with that term that's different. So we have minus 2 times the trace of x b of x transpose. And now just by definition, recall that we constructed b, despite my arithmetic mistakes, to be minus 2 times the sum over ij of d naught ij times xi minus xj, the 2 norm. Right, and that was just by definition. We chose b so that this relationship is true. Okay, now take a look. We have a weird bound on xi minus xj that we got out of the Cauchy-Schwarz inequality. There's a z here, by the way, and a y here. Okay, and so now we can apply our bound. So this is saying xi minus xj is greater than or equal to the expression on the right-hand side. Notice that there's a minus 1 here hiding next to the 2. So this thing is less than or equal to the following expression, where what are we going to have? We'll have minus 2 times the sum over ij. And now we get to write our expression any way that we want. So I'm going to write d naught ij divided by zi minus zj, the 2 norm, times the dot product xi minus xj with zi minus zj. Okay, so notice that now we've got this coefficient, which looks like the element of b up to my arithmetic mistake from before. So in particular, it's very easy to check that this is equal to minus 2 times the trace of x, b of z, z transpose. Okay, so again, basically our inequality here is just following from an application of Cauchy-Schwarz. That's all we really needed in our lemma that we're going to use to derive this Smakoff algorithm. Moreover, remember the equality case for Cauchy-Schwarz is when two things are parallel to one another, meaning that x and z have to be constant multiples as we sort of desired in our original claim. Okay, so again, this is the only term that's different between the left-hand and right-hand side of our inequality here. So what we've verified is this expression here. So essentially, what we're going to do is define an algorithm which is really straightforward. Our algorithm here is going to do the following, which is we're going to take xk plus 1 to be the argmin over x of tau x k. So remember, like really the optimization problem that we wanted to solve was to minimize tau of x comma x over all x, but we're going to have an iterative algorithm where we initialize x0, then we get x1 and x2 and x3 and x4 by solving this optimization problem, where we kind of take one of the inputs to tau and pretend like it's a constant and just optimize over the other one. So again, remember that like what we really wanted to do was to solve min over x of tau x, right? That's what we'd like to solve in an ideal universe, because this is our original problem. That's what we showed earlier. But this is hard, so what we're going to do is kind of take half of the inputs to tau and pretend like they're a constant, just optimize the other half, and then iterate. So I claim that this algorithm is at the very least monotonic. So what do I mean by that? Well, what I mean is that our objective function decreases in every step. So let's see if we can derive that really quick. In particular, okay, so let's say f is the stress majorization objective function. And let's evaluate this at xk plus 1. Right? So we want to show this is less than or equal to f of xk. So by definition, this is equal to tau of xk plus 1, xk plus 1, like that. Okay, so now what do we know? Well, let's see here. So we know that if we change the second argument in tau, things get bigger. Yeah? And we know that we minimized over the first argument. So let's do this in 2 steps. So based on our lemma here, right? So tau of x comma x is less or equal to tau of x comma z for any z. One thing we can do is choose z equal to xk. And what we've shown is the following. This is xk plus 1, xk. Okay, so again, what did I do here? I just computed this upper bound based on the lemma that we proved earlier. Okay, so far we're doing okay. We've upper bounded. And remember that what we're trying to do is to target f of xk. So that's tau of xk. So we managed to engineer an xk here. We need to put one here. But thankfully, what do we know? Well, by definition, what is xk plus 1? Well, it's the min over all x of tau x xk. Well, take a look. So I put xk plus 1 here, and it's tau of xk plus 1 xk. So by definition of this minimization problem, if I put any other x there, the objective only gets bigger. So in particular, this is upper bounded by tau of xk xk, which is exactly f of xk. So what did we show? We showed that our fixed point algorithm, like what I've written on the top of the board here, where I iteratively fix the second argument to tau and optimize for the first, this algorithm monotonically decreases the objective function f. Now, what have I not proven? I have not proven that the x's our convergent sequence. That's a much more difficult proof and one that we won't do today. But at the very least, no step of this algorithm does harm in our overall stress majorization objective function. So that's a good thing. Now, why would I do this relative to just solving the actual problem we want to solve? The reason is that I claim this argmin problem is much, much easier. In particular, one thing we can do is take the gradient of our objective, and what we're going to see is that it's very straightforward to do that. So let me fetch my notes here. So again, if you recall, we have an expression for tau, right? Tau, I'll copy it because I erase it, of x comma z is equal to this constant term plus the trace of x v x transpose minus 2 times the trace of x b of z transpose. Okay, so if I want to minimize this problem with respect to x, with xk fixed as z, then what do? I want to compute, set the gradient equal to 0. So I have the gradient with respect to x of tau of x, xk, like that. Okay, well this is just a quadratic problem. Do you see that? So there's a quadratic term in the middle, the constant term which goes away. And now this is actually linear in our unknown because we're just sticking xk in all the stuff we don't know how to deal with. That's sort of the sneaky part of this algorithm. And so what do we get when we compute this gradient? Well, we get, let's see, so the gradient of this first term is going to be 2xv. And the gradient of the second term is, right, this is a linear term in x, so we expect it to be a constant. And in fact, it's just equal to 2xkb of xk. All right, and this is an expression we can solve for x, right? So at the end of the day, what do we get? We get that xk plus 1 is by isolating it, xk plus 1 is equal to x in this expression, right, is going to equal 1 over, oh, right, so after I plug in our expression for v, remember that's a matrix that we wrote down before, what we'll end up getting is that this is 1 over 2n times xk b of xk, right, that's this term here, times the identity matrix minus 1, 1 transpose divided by n. Let's see if I can make that line a little clearer. Okay, so the way that we derived this was really, really simple. All we did was notice that the form of tau here is just quadratic as long as we keep the b of z transpose term fixed constant. Right, so we have a quadratic term here and now a linear term here. When we take the gradient, we just get basically a least square solution for xk plus 1. So what does this mean? This means that our algorithm, this smack-off algorithm here, in every step, actually doesn't have to do any work. Like, it might feel like, oh, there's an argmin here, so like maybe I have to do gradient descent or something. But that's actually not the case. This argmin is computable in closed form, as we've derived down here, just by taking the gradient, setting it equal to 0, and isolating x. Okay, so what did we show? Again, we took the original objective function for stress majorization and wrote it as tau x comma x for a careful choice of tau, where tau takes 2 arguments. And essentially, we took all of the nonlinear and non-quadratic part of tau and just stuck it in the second argument. Now, first of all, we proved a convenient bound, which is just a byproduct of Cauchy-Schwarz inequality. And we wrote down an optimization algorithm that iteratively optimizes one slot of tau while keeping the other slot fixed constant. And the reason that we do that is that we get a nice closed form expression for what each iterate will be in each step here, which is just closed form. There's nothing to compute here. It's just a matrix multiply. Right. And so finally, One thing that we did check is that the objective function decreases in every step of this algorithm. It turns out with some additional assumptions, sometimes you can show that the technique actually converges. So let's erase the board really quick, and then we'll summarize this in slides too that don't have my ugly handwriting. Okay, so let's summarize what we've done in nicer looking slides. Right, so here we see basically a single step of this Smakoff algorithm. At the end of the day, it's just this formula for xk plus 1 that I've given on the slide here. This is an example of a majorization minimization algorithm. It's a very common approach in machine learning, it turns out. And it at least has this nice objective convergence property that the objective value decreases in every step. We have not verified that the x's actually converge, but I think we often observe that that's the case for this particular technique. I guess we've already proven this bound, so we didn't need to leave this slot here. So there are many different applications of this style of machinery. So another one is graph embedding. So one thing I might do is run the Floyd-Warshall algorithm to compute pairwise distances between vertices of a graph. That gives me that distance matrix D naught, and then I can embed the graph into the plane using this algorithm, and you see the style of result that you might get. For instance, embedding trees, you can see that the kind of tree structures are very easily visible in this style technique. There have also been applications of this to 3D geometry. So for example, if I modify the edge lengths of a triangle mesh, like I want to make the belly of a character bigger, one way I could do that is add to the metric or the edge lengths there, and then try to re-embed using an algorithm like Smakoff, and then it'll expand a little bit. Thankfully, you guys can't see that in this, this black camera here. There are also many other related methods to this that essentially can be tackled with the same algorithm. Another well-known one that's worth calling out is by Salmon, S-A-M-M-O-N, which essentially is identical to this stress majorization objective function, with the exception that it's normalized by D naught. You see there's a denominator in the objective. Essentially what this ends up doing is reweighting the problem to care more about small distances, whereas stress majorization cares more about big distances, right? So here, like, if D naught ij is a small number, suddenly now that term is getting a much bigger weight than it had before. Which means that local structure ends up being preserved better. So we see an example of that at the bottom of the slide here, right? Like the sort of classical MDS maybe clusters some of the nearby points too close together, and Salmon's mapping technique expands them apart a little more. The good news is that the algorithm that we just derived more or less applies to this one, just with some constants adjusted. So I'll let you work that out at home, since I keep getting constants wrong anyway. And now the one last thing to mention in this lecture segment is that we are only scratching the surface. There are so many different techniques out there for Euclidean distance embedding. Here's an entire book just on different algorithms for multidimensional scaling. So if you like this kind of thing, I encourage you to do a lot of digging. People in statistics, data science, and other areas spend a lot of time focusing on this because it's so critical in order to visualize and understand data sets. But with that, we will conclude our discussion in this lecture segment. In the next lecture segment, we're going to think about different ways to embed non-Euclidean data. So for example, if I have data that is sampled from some manifold, then maybe I want to come up with an embedding that preserves the manifold structure rather than just gluing it into space that looks like the extrinsic geometry that I computed. So with that, I'll talk to you next time.